Hi, welcome to today's talk on buoyancy and Archimedes' principle. First, I want to review weight and free body diagrams. First, a free body diagram represents a mass with just a dot, sometimes a box, and then the force is represented by a force vector. The length of the force vector tells you the magnitude. Now, for example, something falling in free fall in a vacuum or neglecting air resistance, the free body diagram would look like this. Here's the mass. Here is the force of gravity or the weight. And we calculate the force of gravity by taking the mass here times the free fall acceleration, 9.8 meters per second squared. With air resistance, we will add another force vector, and notice that the tail of the force vector goes on the object. Once again, we have weight, that's the force of gravity, it's mass times g, and then we have air resistance, some drag. Here's another example of a free body diagram. This free body diagram represents this box sitting on a surface. It is in static equilibrium. Once again, we have the force of gravity or the weight, and then we have a normal force pushing up. Notice that the length of these two vectors are the same. When we do vector addition with these two, they equal 0. Archimedes' principle states that any object completely or partially submerged in a fluid is buoyed up by a force, which we'll call capital B, with a magnitude equal to the weight of the fluid displaced by the object. So B will equal, we're going to call this capital M because it's the mass of the fluid displaced, not the mass of the object that's in the fluid. So the weight of the mass of the fluid that is displaced is the mass times g. What is causing this is the pressure difference between the pressure of the fluid on top and on the bottom. As we saw before, the farther you go down, the more pressure from the fluid you get. Now let's put a mass in there. Let's fill that void, that volume there. And we're going to have two forces on this mass. First, the buoyant force, which we said before was the mass of the fluid displaced times g. Then the weight of the object. The weight's going to be the mass of whatever's in here times g. Again, this is the little m is the mass of the object in the fluid. We don't want to get these two mixed up. We can go back to the diagram that we used before. Again, we had this volume of fluid here where we had two forces, the pressure from the top and the pressure from below. The buoyant force is going to be the mass here of the fluid that's displaced, which is going to be the density times the volume, again, of the fluid times g. A quick review of Newton's second law. If we have a mass and we have a net force on it, then we get an acceleration, where acceleration is the net force divided by the mass. Let's look at a few different situations here. Here, the density of the object is less than the density of the surrounding fluid. If we look at the buoyant force from the fluid, which we looked at before, the density times the volume times g, and then the weight or the force of gravity on our object, which again is going to be rho v times g, this time of the object, the net force will be the buoyant force pushing up minus the weight pulling down. We do some substitution and we take the difference between the two densities, multiply it by that they both have the same volume times g. And in this case, our acceleration is going to be up. This object eventually is going to reach the surface and float. If the density of the object is greater than the fluid, then using the same derivation before, the density of the fluid being less than the density of the object makes this entire part here negative. So the net force is pointing down. It is negative. Our acceleration is pointing down. It is negative too. Now, what happens when this object, once it accelerates to the top, eventually it floats, right? So what happens then is that it's in static equilibrium. The buoyant force and the force of gravity are equal. So the same thing's sort of happening there. Here is the weight of the object. It's the density times the volume times g of the object. On the other end of that, the buoyant force is here, the density of the fluid times the volume of the fluid times g. But it's only this volume here is going to be the volume that is being displaced. It's not this. These are two different volumes here. Hot air balloons work off of Archimedes' principle also. The fluid now is our atmosphere. The volume being displaced is the volume of the balloon. And inside the balloon, you will have air that is heated up, usually from a burner down here. Hot air comes up into here. It is rising. And that is rising because it is less dense than the surrounding fluid. The buoyant force, once this gets hot enough and the density has gone down enough, then you have the buoyant force being more than the weight, and you accelerate up. So what do we know now? According to Archimedes' principle, the buoyant force has a magnitude equal to the weight of the fluid displaced. So it's going to be, we're calling this big M times g, and that big M is not the mass of the object, but it's the mass of the fluid displaced, times g. The net force is the buoyant force minus the weight. That works out to be the density of the fluid minus the density of the object times the volume of the object that's doing the displacement times g. All right. Complete your Cornell notes, rewind, and review as necessary.